This video is about the process of making the prototype electronic boards for the Steering Pad 900F, the top, the bottom, and the connected components. Before I start, I just want to say something very important. This is not a guide or official instructions on how to build this controller. This is more like a documentary. I'm just showing how I built mine. This video is about a personal project that I built solely for myself that I'm sharing for documentation's purpose only. I'm sharing what I did, how I did it, and why, but I'm not telling you to do it or encouraging you to follow it. Also, I'm not an electronics or mechanical engineer, and this is just the result of a curious person exploring prototype electronics and 3D printing. If you decide to replicate or adapt this project, that's completely up to you, at your own risk. I cannot take any responsibility for any damage, injury, or problems that might happen to you during construction, modification, or use of the devices you make. Please handle all tools and electronic components carefully, follow basic safety procedures, and double-check everything before powering it up. And of course, if you are unsure about anything shown, just ask in the comments. I will do my best to explain what I'm doing in the video. To help you follow along, I have prepared a document you can download. It includes a detailed representation of everything you need to know if you want to try to recreate my process. The diagram is drawn to scale, so if you print the page at 100%, it should match the exact dimensions of the boards. Let's go over what's in the diagram. This is a top view representation of both sides of the board. Don't forget, you can see the top and the bottom aligned. The top side is where the components are placed. The bottom side is where the copper lines and the soldering points will be. As you might have noticed, I have rotated the board in this specific direction, to the side. I always rotate the board the same way to keep the references. This ensures the copper lines number, from top to bottom, is the same as in the diagram, but the hole count will be mirrored. In other words, if in the diagram you count to the right, on the physical board you count to the left, and vice versa. That's a rule you should always follow. Now, let's take a closer look at how you can read the diagram. It's color-coded and each color represents something specific. I will start with the bottom side of the board. This side contains the copper traces and the cuts of those traces. The traces are represented in gray and the cuts are represented with the red axis. If you look at the finished board, you will notice that some of these copper lines are cut. For example, here and here, you can see the cuts. These cuts are marked on the diagram with red axis. When viewing the board from the top, the gray lines represent the copper lines underneath, and the red axis where the cuts on the copper line is placed viewed from above, like if the board was transparent. Again, keep in mind, to perform the cuts, you turn the board over to the side and mirror the positions. You will count in one direction on the diagram and in the opposite direction on the actual board. These cuts marked with the red axis don't need to go through all the board, just enough to break the copper connection from one side to the other. Now, the green and dark blue lines in the diagram represent the wires and components on the top of the board. The green lines are wires, so this wire corresponds to this wire, and this wire matches that wire. The blue elements in the diagram represent the components. For example, these two shapes correspond to these two switches here, and these two rectangles represent these two resistors. The first step in making our PCB is to cut the board to the correct size following the magenta lines, which represent through-hole cuts. You might notice I have two screws here. This helps keep the board steady while I cut, so it doesn't slip out of place. To measure the size of the boards and place the cut, you will need to count the dots or holes from a reference point up to the cutting line. Another unbreakable rule: you always include the reference point and the target point in the count. Count the number of holes from the reference point, which in this example is the first hole, until you reach the cutting line. Then align that point with the screws and cut from one hole to the other. I use the holes as a guide because the knife will naturally jump from one hole to the next. You might also notice that the cutting direction is aligned with my natural arm's pulling direction to avoid slipping sideways while cutting. So, this will be the position of the board. Remember to keep the board with the correct rotation before cutting. Don't accidentally rotate the board and cut it in the wrong direction. Now let's count the holes and make sure we are cutting in the correct spot. Let's count together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and 22. The cut will be on 22. So now I just need to count 22 holes on the actual board and mark the cutting point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. The cut will be on number 22. I will make a small mark here and another on the opposite side. This is the column of holes where I will make the cut. Having the cutting line and the board aligned with the holding screws, I place my X-Acto knife directly into the first hole, not outside of it, and gently pull the blade until it jumps to the next hole. See, the blade follows the cutting line. I pull it without applying pressure. I'm not cutting yet, just scoring the surface to create a guiding groove. The first pass should always be slow, because if the blade slips or follows the wrong direction, it will want to repeat that path the next pass. Once the groove is in place, I can go over it again, this time applying a little more pressure. Now the board is deeply scored, I can open the beginning of the cut. This side is done, but before I snap the board, I also need to score the copper traces or they might tear apart and get damaged. Again, the first time you go slowly, letting the blade jump from one hole to the next, and when the scoring is done, you can apply more pressure. Once both surfaces are cut, you can simply snap the board. That's cut number 1. Now let's move to the next cut. The cuts are numbered and you should respect the order of cutting to facilitate the process. And the process is the same as before. Count the position, score it lightly, and then cut deeply on both sides. Now I'm doing cut number 7, which is a bit different. This needs to start in the middle of the board and run outwards in both directions to maintain the L-shaped board intact in the corner. Let's begin by counting how much space we need, going from one side to the center. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. It's 17 holes between the previous cut and the next cut. Let's measure where the corner should be. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Let's count from the cut as the reference. 1, 2, 3, 4, 5, 10, 15, 16, 17. So this is where the corner of the L-shaped cut will be. And since I don't want to cut past these edges, I will place the blade on this hole and cut it outwards. From the same starting point, I cut it the other side. This should start to break along the lines, but I will go slowly to avoid spreading the snapping past the corner. Now I have my L-shaped board. Let me place the other one on top to compare. And this is where I found I cut the board wrong. It was not a fatal problem for the board because I cut the board bigger than what I needed and there was still material to remove. I counted 19 holes on the diagram but somehow just 17 when I went to the actual board. I may have been confused with the previous count that was 17. Correcting the problem is removing more material and the board can be salvaged. If the cut made the board shorter, this board would not be useful and another one had to be cutted from a blank one. So, be careful while counting, marking and cutting. All the necessary cuts are now complete and these are all the boards needed. These two for the pedals, this one for the steering sensor, this one for the turn signal buttons, this one is the main board, and this one is the top button board. The rest are not necessary for this build, but you can reuse them on other projects. These circles, being magenta, also represent that they should go all the way through the board. These are 3 mm in diameter drilled holes for the screws that will secure the board later. The drill is centered on a hole, so the position just has to be counted as before. Same goes for this one. Find the center and drill. These boards also require drilling, so you can mount the sensors properly inside the mechanism. The cuts made the material at the edges to expand outwards. If I sand it perpendicular, the problem will increase before it's solved, and then the board will be too small. Instead, I will sand them at a slight angle. 4 light passes, no heavy pressure, and that's already smooth enough. This needs to be done on all edges. This process needs to be repeated for all the boards. The inner sides of the L-shaped board needs a slightly different approach. Because I have the sanding paper glued to a board, I can just use the edge of the board and sand like this. This main PCB goes into the PCB board base 3D printed part. It should fit without any force, with the copper side down, but also not too loose. It will probably be a tight fit and will probably need some more sanding to fit without effort. If it fits perfectly, the board is ready. The board that goes on top doesn't have any tight fittings. It will be secure by the connectors and the screw of the ignition key, so it's already fine. It will be mounted aligning this hole with the one on the 3D printed part. The sensor board needs to fit the tool that helps align the Hall sensor in the right place when soldering it. The boards need to fit the tool without force, so it might be necessary to sand them a bit until they fit. The turning signal buttons board has to fit the steering wheel base 3D printed part, and it also might need some sanding, but this one already fits perfectly. The next step is to mark the through all 3mm drills for the screws. I'm marking the location with a pencil. You might see it in the reflection. I'm using a 3mm drill bit. The place is already marked, so with the drill on top, I start rotating gently and I get it going. The drill aligns itself easily because of the hole below. Just make sure the board doesn't rotate. You can use a drill machine, but drilling by hand is actually quite easy. I also drill a little from the other side just to clean the hole. That's it, some perfect 3mm holes. All of these green lines represent wires that need to be cut to length. To prepare a wire, I need to strip both ends to expose the metal and ensure it has the necessary length to reach the soldering points. It's normal to cut first and strip later, but in this case, I will do it differently. Stripping the ends of a very short wire is really difficult, even with the correct tools, so I had to use a different method. Let's say we need a wire with 3 holes in length. It needs metal on both ends and plastic in the middle. First, I calculate the length I need on both sides and remove that section of plastic all at once. To do that, I grip the plastic with my cutting tool, not strongly to cut the metal, just firm enough to hold the insulation. Then I push to slide off the insulation without damaging the metal. Now I have one long exposed metal section, enough for both ends of the final wire. Next, I measure out the correct wire length, in this example 3 holes, and I mark the spot. Then I press lightly with a cutter, again not to cut through, just to grip the insulation, and gently I do this lever motion with my thumb to slide the insulation without removing it completely. This way, both ends are already stripped with the plastic in between. Only cutting is necessary. This is very effective with all length of mid and short wires. When the wire is cut from the spool, bend down the ends and it's ready for soldering. It does take some practice to be quick and some wires don't come right at the first try, but I'm sure you will finish it faster than you think at the beginning. Avoid cutting and soldering each wire at a time because soldering irons do not like to be idling, so I'd suggest cutting and verifying all wires first. Use the diagram to measure, bend and mark the cutted wires and place them organized on a bit of foam before you jump into the next step. If the wires have curves and bends, I follow those curves while measuring, but the wires have to be straightened before the final slide. You don't need to have the exact shape from the diagram. You just need to make sure the wire connects the correct two endpoints. And that does not go below some component that needs to be flat with the board. Personally, I like to shaping them to follow the diagram. It gives the board a cleaner look, but functionally, as long as you connect point A to point B correctly, the shape doesn't matter and it will work just fine. Don't forget that what is represented on the diagram is the insulation section only, because the metal ends will bend down, go through the board, and be soldered below. I also always try to keep the wire flat against the board. If it's a bit crooked or the shape doesn't match exactly, that's okay, but it needs to be flat on the board. If you want to shape the wires precisely like in the diagram, you can print the PDF at 100% scale. That will give you the exact size guide to match each wire's path. This is a true-to-scale version, so it should align perfectly. You can use it to bend each wire to match the printing, and it has to be correct on the board. All these wires took me about 2 hours to cut and shape. The green lines represent the wires on top, but there are also, let's say, wires on the bottom as well. These bottom wires are the copper tracks. They go from one side to the other, but not all of them can be so long, and the red axis represent where to cut them. You will see in the diagram that some tracks need to be cut in specific place to isolate both sides of the track from each other. Some of them are even cutted more than once, and that's the next step, making sure that the cuts in the copper tracks follow the correct layout. This diagram only shows the cuts. Here's the board we cut and drilled earlier, and if aligned, it matches the diagram. To make this track cut, remember, they are always done on the copper side of the board. So, to do them correctly, I will place the board here and flip it sideways. Bottom is bottom, top is top, but left becomes right and right becomes left. We are mirroring the board with the flip to the side. Now we use the same technique as before, count the holes and make the cuts. Let's do this cut over here. A cut shown on the right side of the diagram will be on the left side of the board. Start counting the white dots, including the first reference point and the dot with the red X in your count. 1, 2, 3, 4, 5, 6, 7 to the right in the diagram, 1, 2, 3, 4, 5, 6, 7 to the left on the board. Now we go to that spot on the board and drill lightly, not all the way through the board, just deep enough to cut the copper track, separating the left side from the right. And now this part is done. Some cuts can be corrected with a bit of solder if you make a mistake, But if you cut too many or get the layout wrong, you might need to start over with a new board. So, always count careful and use a reliable and verified reference point to start counting. Again, always include the reference and the cut in the count to make the method consistent and reliable. When one cut is done, mark it on the paper to make sure you don't forget anyone. Repeat the process until all X's are correctly cut and marked. At the end, I clean up the edges of those cuts with the sanding sponge. I verify all cuts with a regular multimeter in continuity mode. That's the one that beeps when the 2 points get connected. Touch one side of the cut, then the other. It cannot beep. If it beeps, there is a connection. See? No connection. It connects here, but not here. This side has continuity, this one doesn't. And that's the purpose of the cuts, to isolate and create two independent copper lines. I will repeat the process for all the remaining boards using the same technique as before. I also verify them by jumping to the next line and making it beep on purpose to ensure two things. The multimeter is still working and there is a good contact with the probes. If I only touch the separated sides and it never beeps, how do I know that the probes are okay? This is just a double check at every test. It beeps on one side but not on the other. I have the boards with the tracks isolated and all the wires ready to solder, but there are two components that need the board clean to align them correctly, using the flat face of the table. I'm talking about the connector to attach both boards together. These pins will be soldered directly on the copper side. This is probably the most difficult part of the entire project, getting these pins aligned perfectly and soldered properly. I have a specialized tool to help with the alignment and another to help prepare the parts. The first step is to prepare the pins for soldering. If you look closely at the pin's stripe, you will notice the plastic has a little indentation. One side is flat, but the other has a U-shaped groove. This U-shape goes towards the board. So I place it in the pin puller tool with the U side facing in. The long side of the pins should be out of the tool. Now I press until all the pins slide into the plastic using a vise. It's also possible to do it without a vise. This needs to be done on both stripes. The first connector goes here. 1, 2, 3, 4, 5, 6 to the left on the diagram. 1, 2, 3, 4, 5, 6 to the right on the board. 1, 2. 1, 2. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. Again, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. This first pin lands on a cut, and that matches exactly what we see in the diagram. Now, not all pins will be soldered. The ones that land on a cut don't have copper to grab, and that's okay. It's really important to solder the connectors straight. It can't be crooked, or tilted, or leaning forward or backwards. It must be perfectly perpendicular to the board, and that's where the pin holder tool comes in. The board is oiled against a flat surface to make sure the pins don't stick out past the board top face, keeping the connectors with the correct depth. and the tool will make sure the pins are at 90 degrees with the board. With this setup, I can solder them. This soldering iron has a sponge, some do, some don't. It's used to clean the tip of the iron when it's covered in excess solder or burnt residue. If you don't have a sponge, a wet paper towel works too. It should always be wet, even the sponge. Now, to solder, you need to heat up the pin and the track first. Then you apply about 1 mm of soldering wire. This soldering wire already has flux inside, so it cleans while it melts. If your wire doesn't have flux, you will need to apply flux separately before soldering. The way I do it, I heat for 2 seconds, apply the solder, then remove the soldering wire and the iron. I make sure I'm touching both the pad and the pin at the same time. 1, 2, solder, remove. And that's it. The solder will flow to the heated metal parts naturally. Before soldering the rest, I check the alignment. If it's not straight, this is the time to adjust it. You don't need to worry about melting the tool, it has a diagonal cut that keeps the heat away from the plastic. So, it's safe to solder while the tool is still in place. Don't forget, no pin should touch another pin. If soldering feels a little bit difficult, soldering paste can be used. I like to dip the tip of the soldering wire into the paste directly just to coat the wire slightly. That should be enough. With the pins in place, I remove the tool and redo all the soldering points just because it's better to apply heat from one side and solder from the other, to make sure the soldering point is consistently connected. And that's it. If you ever need to remove excess solder, for example, if you accidentally breach two pads, use desoldering copper mesh or wick. Just place it on top of the solder joint, press the soldering iron on top, and it will absorb the extra solder. Now the pins are no longer touching each other. This, in my opinion, is the most difficult component to solder, because you are soldering on the same side where the component is placed and the component itself gets in the way. All of the others will be much easier. When using soldering paste, some residue may remain on the board. It's not enough to cause a complete short circuit, but it can make a high resistance connection interfering with the signal's transmission. So I clean it with a bit of acetone. Using a toothbrush with acetone, I scrub the board to make sure the area is clean. Sometimes the residue crystallizes and gets hard. That is the worst problem and it needs to be scraped out with a sharp tool. All the problems I had in the past with this kind of boards was the laziness to clean. The gunk is removed and the circuit works fine. You should do this on all gaps to make sure there's no residue left between them. You need to clean with acetone and with the sharp tool before you push the plastic parts down. Pushing them back up will remove some of the copper traces and ruin the board. So make sure the board is clean before you push down the spacers. Now the plastic part can be pulled down using the same tool as before. Here manual force will be enough, the plastic is no longer tight. Just align the tool in place and pull it down. A bit of manual pressure is all you need, just press until you won't go further. Be careful, don't clamp it or the metal pins won't fit the middle properly. The plastic should be against the board as much as possible with the solder inside the U-shaped groove. The process of soldering the wires is pretty straightforward. I start by checking the wire's dimension and pick up the correct one. Then I count the position of one of the ends and roughly place the wire. Then I proceed to verify both ends, to check if they are where it's supposed to and correct if necessary. Then I turn the board over and solder the wires. Sometimes the wires fall when turning the board over. I use the tweezers to hold one of the ends, or I bend a little on the other side to prevent that. To solder, the process is the same as before. Hit the pad and the wire, melt the solder, and remove. 1, 2, solder, remove. 1, 2, solder, remove. And that's it. The wire is now secured in place, flush with the board. If you take a closer look at the soldering points, you might still see a bit of soldering paste residue between the tracks. But that's okay for now, I will clean the entire board at the end. Now let's take a look at the resistors. 10 kiloohms, 22 kiloohms, and 33 kiloohms. If you are unsure of the values, use a multimeter. Set it to resistant mode, the one with the ohm symbol, and measure the resistor, touching each leg with each probe. Don't touch both ends with your fingers at the same time, that can split the reading and give you a false value. And there it is, 10K, 10 kiloohms. The gold stripe means 5% tolerance, so the actual value could be slightly off, maybe 9.5 to 10.5. In this case, you want to find 3 resistors with the same value, even if it's not 10K. The important thing is for them to be equal to each other and roughly around 10. So these are my best 10K resistors. I need 3, so let's pick the 3 closest to 10. Let's solder them, and then I will move to the others. The resistors don't have polarity. You can solder them in either direction, no problem. You just need to insert them into the correct holes. The resistor spans 4 holes in length, and I will bend the legs right beside the body to keep it in size. These long legs can be annoying. So, normally when a component has long legs, I trim them right after soldering by placing the cutting tool close to the soldering joint and holding the wire with my index finger, so it doesn't jump out towards my face when I cut. There! The legs are magnetically annoying. That's it. All the 3 10K resistors are soldered. They might be hard to see clearly on the video because their colors blends in the background, but they are there. Now let's move to the 22K resistors. It could also be 20, but usually you'll find 22K in stores. Let's measure them and pick the best matches. The process is the same as before. Try to get 4 equal resistors as close as possible to 22 and use those. Once again, use the same process to select and solder the 33K resistors. It is more important to be consistent across all of them instead having them match the list of materials. The code doesn't differentiate which resistance is being read, it just expects a certain range, and when the code is set up, the value will be used on all of the inputs. It wouldn't be impossible to handle different values in code, but I'm already pushing the ProMicro memory to the limit and it would require more unnecessary calibration. This button resets the ProMicro in case the controller gets stuck and does not communicate with the computer. It is only necessary to force upload the code. This happens when the code has some bug that prevents the Arduino IDE from seeing the microcontroller, and uploading a fix is very difficult if you don't reset it when uploading. This button is not mandatory if you are not planning on experimenting with the code, but if you feel you can improve it, add the button. This button has 4 legs, 2 on each side. They are placed on the sides and the button connects the left to the right. Be careful of the orientation because if you rotate the button and force it at 90 degrees, it won't work. The legs must be aligned to the sides, not top and bottom. One of the legs, the top right, will sit on a track cut. This is okay, but it means that the pin doesn't need solder. This button creates contact between pin 2 and pin 3 when pressed. Let's test it. Yep, it's working as expected. The first operation I do with the display is to solder the pins to the display. You also have this helpful pin-out reference in the diagram, which tells the function of each pin on the components. For example, for the display, from top to bottom, the first pin is SDA, second is SLC, third is VCC, and fourth is ground, respecting the position on the diagram. That's the exact order and orientation in which the pins should be placed on the actual board. So, if your pins are not in that order, you are probably soldering the part in the wrong direction. Don't do that. The display connects at position 1, 2 from the left side at the top line. So, this is where I mount the display. But if you look closely, you will notice the screen is tilted. It is not parallel to the board and it should be. To fix this, I need to raise the screen slightly. The correct height is exactly the thickness of 2 plastic pin header spacers. So what I do is take 4 more pins from the strip and remove the pins to use just the plastic spacer on the display connector, raising the display to the correct height. If you don't have extra pins, you can also slide the plastic down after soldering the pins to the display to hold the distance. To remove the pins, I just pull them out one by one. Then I take the plastic spacer and slide it onto the long side of the pins. I use the pin alignment tool to press the pins down into the plastic. With that in place, I solder it. First, I solder the pins to the display. Then, once that's solid, I solder the display to the board. I use an alligator clip to hold the pins while solder. The pins go from underneath into the display. I place the display and solder just one pin first. This is so I can check if the angle is at 90 degrees. If it's not, let's simulate it. If it's tilted, I reheat the solder and gently push into the correct position. Just remember, don't push the heated pin. Then I solder the rest. I use the tool underneath just to raise the board a little and keep it parallel to the table. It looks pretty good, nice and clean. The display is now firmly in place. If I press the right side of the display, right where the button is, I press the button underneath and actually activate it. The switches have three pins, C, N, O, and N, C. That stands for common, normally open, and normally closed. In the diagram, I can see the lever direction. The square pin represents the C pin, the common pin. It's the one closest to where the lever meets the switch body. When placing the switch onto the board, I make sure the levers are pointing in the correct direction. I mount all the switches into place and hope they don't fall when I rotate the board to solder. After making sure the direction and positions are correct, I solder all of the switches at once. And I believe it's done. Let's not forget to clean it and check with a multimeter if necessary before connecting. It took me around 2 hours to make the entire board while filming and explaining, so it should take less. The first element to solder on this board is the wires. The process is the same as before, but extra careful is advised because the references get complicated with the bent wires. I'm using three 100K resistors to connect the sensors to the ADS 1115. Each sensor has to be calibrated individually and the resistor values don't have to match as in the buttons board. Just keep them inside the 5% tolerance. The next flattest component is the L-shaped connectors. The L-shaped pins will be soldered in order to make the pins and the connectors go out horizontally. This is to prevent the connectors and cables from rubbing against the steering wheel and the buttons board. I need a 4-pin connector here, but I'm going to intentionally remove one of the pins. I also need another 4-pin here and another one here. Here, up the top, I will use a 2 plus 3-pin connector, which I will make using a 5-pin strip. That makes soldering easier. I cut them from a long strip of pins, breaking them manually. I just place my nail over the breaking point and snap it. Super easy. Now I have three 4-pin sections, one for each of the three sensors connectors. If you look at the blue representation in the diagram, you can see some lines coming out of the connector. They show the direction the connectors should point. Following this information, I remove the missing pin on the diagram from the 4-pin connector. I hold it firmly and just push the pin until it comes loose. Now I have a 3-pin connector with a 4-pin span. I'm doing this because that missing pin is where the positive pin go if someone connects the connector the wrong way. That way, if the connector is connected backwards, the positive pin ends up in an empty slot and the sensor does not get damaged. If data and ground are reversed, nothing happens to the sensor. But if the positive is connected to something other than the positive pin, the sensor will get damaged. Now, this connector goes right here. You can see that the isolated pin actually aligns with the first resistor. Let's move to the second connector. This one also has a pin removed. And the isolated pin aligns with the second resistor. The final connector also needs a pin removed, and it goes somewhere around here. The isolated pin connects directly to the third resistor. Lastly, I have this 5-pin strip, which goes straight to the top left corner of the board. Now I'm ready to solder. I soldered down just one pin on each connector first, then I check the alignment. If everything looks good, I solder the remaining pins. All connectors are now properly soldered and looks great. These female headers are where the other board will connect, and they need to be soldered on the bottom board. Those outer rectangles, the ones with the open blue little circles, represent the female connectors. The microcontroller sits in the middle. I count to confirm the placement. 1, 2, 1, 2. It goes right here. The last pin sits just next to the wire, as you can see. This connector might not sit perfectly perpendicular to the board, but I will show you how I fix that in just a moment. The other connector goes over here. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, it sits right next to the wire, aligned just like the other one. I place them carefully. What I do is place them roughly in position, then solder just one point to hold them. Actually, I purposely solder them wrong just to demonstrate the issue and a fast way to solve it. So, they are both crooked. They are not perpendicular to the board. If I just push the component into the right position, I can damage the pin or the copper track. To properly fix this, I remelt the solder by gently heat the solder joint and push the connector against the board. Because it's a rectangle, it naturally settles flat. I can feel a sort of clicking into place. Pushing it slightly makes it align to 90 degrees by itself, and I can even feel it sitting flush against the PCB. I have created a small solder bridge here, a connection that shouldn't be there, but I will clean that after all the pins are fixed in place. Otherwise, this might get loose. I also check if the board fits together and line up as expected. I don't force it now because removing it before soldering all the pins might damage something. So, all the pins are soldered properly. Before moving on, I test for electrical isolation. If anything bips, I check the diagram to make sure it is supposed to bip. Some pins might already be expected to be connected with the wires. I go line by line, These 2 points are supposed to be connected. Perfect. Now I place the capacitor. I'm using a 50 volt 10 microfarad capacitor. It's possible to go a little higher in microfarads or slightly lower in voltage, but this one worked just fine. This type of capacitors have two polarized connectors. When it's new, one leg is shorter and the other is longer. The shorter leg is the negative, but if you are using a salvage capacitor, the legs might be the same length. The way to identify them is looking for the stripes with the minus signs. That marks the negative side. Here on the board, the negative pin goes to the second line and the positive goes to the top line. It should just fit next to the wires across a diagonal path. So, negative on the bottom left and positive on the top right. I position it like this. I leave about 1 free millimeter, then bend down the negative pin. The negative leg is bent and goes here. Now the positive leg needs to be bent a little further so it can reach the top track. Here is how I do it. With the negative pin in place, I use tweezers, look from above, and grab the exact spot where I need to bend the positive leg. Then I remove it and bend it precisely until it looks something like this. This capacitor needs to sit at a 90-degree angle, flat against the board, to avoid touching the solder points of the buttons board. See, something like this. So, when both boards are stacked, they stay separated. Some capacitors might be thicker than this one, but they will still fit the available space. Now I cut the wires and start thinking about soldering the microcontroller. It's very easy to solder the microcontroller backwards. It still fits physically, and the USB port will still face outwards, so it is an easy mistake to make. I always check the labels. Here you can see 0, 1, ground, 2, 3, 4, 5, 6, 7, 8, 9. And those are the exact same labels printed on the board. In my case, I already fixed the next issue earlier, but I will explain what you can expect. The microcontroller doesn't fit into the space the first time you try. The board is just a little too wide. I solve it by sanding it on both sides just to clean the rough edge. I don't apply much force, just enough to clean the side. If it drops into place, it's ready. To solder the microcontroller, I do the same thing as I did with the display. First, I hold the pins in place, then I align the microcontroller on top, making sure all the pins are in the correct position, and solder just one pin. I let it cool and check for alignment. It's not perfectly straight, so I just eat it slightly and gently push it until it's in the right position. Now that it's aligned at 90 degrees, I solder all the remaining pins. The microcontroller sits here between the female headers. with a USB port pointing outwards. I press it down until it's fully seated. Once it's soldered in, it will be very hard to remove. So before I do that, I connect it to the computer to make sure it's not dead. Looks good. And I also check that the wires below are correct. They will be underneath the microcontroller that, once in place, will block the access to them. If something is wrong here, now is the time to fix it. I'm checking, and yes, all the wires are in the right place. Everything still fits. Perfect. Now I will talk about the orientation of the Pololu driver and the ADS converter. On the Pololu driver, the components are on top, but the labels are printed on the bottom side. So pin O2 is on the left, and it should be on the left. Always confirm the correct orientation. If I rotate it, that's wrong. Also, these pins are square and they indicate the ground pins, so this should be down, as in the diagram. So the Pololu goes like this. The components have to be visible and the square pins align down. The ADS module is different. That one must be soldered with the components hidden from view. They face the prototype board. So A0 is down and A3 is up to the right, but as you can see here on the actual PCB, 0 is up and 3 is down. If it's not the same as in the diagram, rotate it until it matches. In the diagram, I have 3, 2, 1, 0 on the right. This means the chip needs to be rotated and placed like this. You will also notice that the labels 3210 are printed on the underside of the module, and that makes it easier to check. On the left side, there's SDA, SCL, ground, and VCC, also labeled clearly. In this project, this PCB needs to be soldered with the components facing down. That means I soldered the pins along the sides of the components, like this. Let's solder it. I'm holding it in place. Okay, it's looking good. I was holding it with a wire while the solder was cooling, and that forced the alignment to be at 90 degrees by seating the board on the pin's plastic spacer. That's cool. Let's solder the rest. Now I put the component on the board. It needs a little push to fit. You should have A3 at the top right aligned with the second pin of this connector, but not connected. Let's confirm. That's correct. A0 at the bottom right should be connected to this resistor. A0 is connected to the resistor. VCC should be on the bottom left. VCC is at the bottom left, and that's it. The board seems to be well orientated and in position. Let's solder it. It looks good. The pins should be separated. Well, actually, these two over here are touching. You can see some solder in the middle. I just pass the soldering iron in the gap, and because the solder tends to grab hot metal, it went to the correct positions by itself, without the need of the desoldering wick. Okay, now they are not touching. None of these pins should ever be in contact with one another. And the ADS 1115 is done. This is the chip responsible for converting the analog signals from the pedals and steering into digital information. That's then read by the microcontroller and transformed into joystick access data. If you don't have the Pololu driver to control the motor, you can leave the board like this and you won't have to do anything else, but it will still work as a joystick input device. You just don't have force feedback. If you have the Pololu, great, let's check the pins. Make sure the components are facing up. Labels and pins go down, components stay up. Let me hold it in place. Once I have it at 90 degrees, I will refer again the diagram. The square pads are on the bottom, those are grounds. So these pins should face downwards. Now let's count the position. 1, 2, 3. And it should go around these two wires. So 1, 2, 3 around the wires. Let me place it first, then I will show it more clearly. Let's count again to confirm. 1, 2, 3. Right around the wires. And the ground pins are facing down. Let's double check one more time. Yes, ground is down. 1, 2, 3, confirmed. Let's solder it. And the board is ready. Now, after cleaning a final inspection, I'm visually inspecting between the soldered lines, using the reflection of the light to make sure there are no soldered bridges or blobs connecting pins. If you have experience, you will be able to spot issues immediately just by looking at the board. If not, inspect it carefully. It looks very good, and here is the entire setup fully aligned and connected. To assemble the sensor's PCB, I'm going to follow these diagrams. I'm going to need three 49E Hall sensors, these small boards. For the steering wheel sensor, the steering sensor aligner tool is needed, and for both pedals, the pedal sensor aligner tool is needed. If you take a closer look at the sensor, it has a flat side and a chamfer side. You can see the flat side on the right and the chamfered side on the left, where the name 49E is engraved. That chamfered side is the front. I will start with the steering wheel sensor. This tool is used to hold the sensor at the right position. The sensor is placed inside. The pins are aligned with the three center holes of the PCB, and everything is pressed together until it's flat. Once the board is flush with the tool, it's ready to solder. This tool assures both the correct distance and the correct position of the sensor. Be careful not to place the sensor backwards. The chamfered side, the front side, should always face right, as shown in the diagram, away from the gap of the wires. The gap for the wires should be on the left. Also notice that the sensor is not centered on the board. If you look closely, pin 3 is aligned straight to the body of the sensor and pin 1 is tilted slightly outwards. That's the shape you want to achieve. It doesn't need to be exact, just enough to fit properly. I place the sensor chamfered side to the right, put the legs into the three centered holes, and press it down firmly. I make sure it sits well, then solder it. I'm using a little bit of soldering paste just to avoid heating the plastic too much. This way it will solder quickly. That's it! The sensor should now be placed at the right angle, position and distance from the board. The wires will go to the component side and should fit the tool gap for them, exiting to the left. 3 wires, 1 per sensor pin. I place and press everything down again using the tool to solder them in position. This is the exact look of this component. Sensor facing right, wires exiting to the left. The brake and accelerator sensors are mirrored. Why? Because they are installed on opposite sides, but need to face the same direction regarding the magnets. Let's start with the brake pedal. Here, the chamfered side, the front, should face left. I put it into the tool and you may notice it tends to pop out a bit. That's just the legs pushing back. I need to adjust the band slightly to help keep it in place. And now, solder it in position. Eventually, this board will be mounted just like this. This means there's no space for the wires to go underneath like in the steering sensor board. In this case, I'm going to solder the wires directly on the copper side. I cut 15.5 centimeters of wire, and now, to make sure the solder holds on the first go, I will apply a little soldering paste directly on the wire. I just scrub it slightly, just to coat it a bit with paste. Now I had a small blob of solder on the tip of the soldering iron and solder the wire in place. The soldering paste will melt, cleaning the pad and the wire, and the blob of solder in the iron will grab them immediately. Done and perfect. When removing the soldering iron, I have to hold the wire in place for a bit while the solder is still melted. I need to wait for it to solidify first. All three wires look good and connected. The hole in the middle is open, but that's not a problem. This sensor is ready to clean. Let's move on the accelerator pedal. In this case, the chamfered side, the front, should be pointing to the right. I will place the sensor in and everything else is the same as before. For the accelerator, I need 18 centimeters of wire. Now, I need to solder them like this. Soldering done, and that's it. Now, looking at both sensors at the same time, the brake pedal has the wires going to the right. The accelerator has the wires going to the left, and both front faces should be facing each other. Now let's solder the wires to the motor. I need the motor with a red mark marking the positive pin, an 100 nanofarad ceramic capacitor, and two 20 centimeter wires. I remove the insulation from the wires to solder them on the motor pins. Be careful not to solder the wire touching the metal of the motor. It should only touch the pin. I'll bend the wire slightly to make it easier. Now I'm using the motor shaft to help hold it in place, although it might cause the motor to rotate. Let's see. Anyway, with the bend pointing down, it should look like this. And a small bit of solder to the wire, same technique as before, and soldering it in. Done. Now the other side. The two wires should come out in the same direction, more or less aligned with the positive pin. It doesn't need to be exact. Same thing, position, solder, let it cool. Now I will try to solder the capacitor. This is a ceramic capacitor and it needs to connect to both wires close to the motor. This one does not have polarity, so it can solder in either direction. I will start by soldering one side, and the wire fell down. Because the wire has no other holding point, as soon as I melt the solder, it will become loose, and gravity wins. I can use another alligator clip to hold it, but I don't have it. So in this case, I need to hold the wire in place with another thing while soldering. I'm using a piece of tape to do the job. This is their natural position. I will secure them like that, or they will come loose anyway. Once they are held in place, I solder the capacitor. Now both wires and the capacitor are connected. I can press it down gently, making sure the metal pins don't touch the metal casing of the motor. And that's it. I'm trimming the excess wire, removing the tape, and the motor is ready. Now that the wires are aligned correctly, I can measure and cut them to length. For the turn signal buttons board, I need a short wire to connect both ground pins, 2 switches, and 3 11 cm long wires. Let's start counting positions. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Second column. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. As you can see, the square pad is towards the middle, so this should be placed like this. I'm almost done. One of the wires goes to ground. It's the one in the middle, right here. Then one wire for each center pin of each switch. This one goes out straight. This other one bends slightly to the right, then up. I use the tweezers to help with the shaping. There's a plastic component that sits here, so it needs to have this space available. The third wire, same idea. I bent it slightly to the right, then left, so that all 3 wires come together roughly like this at the right side of the board. Now I have turning signal, brake, accelerator, steering wheel sensor, the motor for the force feedback, the bottom board, and the top board. The last thing missing now are the connectors for the ends of these cables. And that's the final step. To assemble the connectors, I will need some of these metal pins. They will go inside these plastic housings. 3 headers of 4 slots, 1 of 3, and 1 of 2. You will notice a little arrow on the headers. That's pin 1. The metal pin goes into the larger holes from the back and locks into the header. Once the pin clicks in, it can only be removed by lifting the tiny plastic tab inside. This crimping tool has spring-loaded clamps. If you listen, it clicks. It won't open unless you manually release it or finish the crimping with a hard press. And then it opens. Now, to prepare the wires, I need to strip around 2 mm of insulation, just enough to reach this middle section here on the metal pin. The back part will clamp onto the plastic, and the metal part will make electrical contact here. I break these pins off from the strip It's easy, just bend it until it snaps. I place the cable like this, with around 1 mm of insulation inside in order to allow the back tabs to grab it. The front tabs will grab the bare wire, assuring electrical contact. It should sit flush with the tool. Now I insert the cable just enough. If you are unsure, you can even mark 1 mm on the cable so you can see where to stop, but practice will give you confidence. Once everything is in place, I crimp it down until the tool releases. At the end, it should look something like this. The plastic is clamped, the bare wire is connected, and it doesn't slide out. Now I have to repeat this process for all the cables. Once that's done, I can start inserting the pins into the correct positions of the headers. I will start with the sensor for the steering wheel. Looking at the connector, with the chamfered side up, this wire, the red one on the diagram, coming from the sensor's pin number 1, goes to the second position on the header. So, pick up your connector and insert the pin with the gap facing up on the second hole until it clicks. Pin number 2 of the sensor, the middle wire, is ground, represented with the blue line. This goes to the first hole in the header, and the remaining wire goes to the other corner. So, in this configuration, it is positive, ground, and signal. For the brake pedal, pin number 1 from the sensor goes to header place number 3. The ground pin of the sensor, the middle one, goes to header place number 4. And the signal pin from the sensor goes to the other side of the header. Same thing for the accelerator. Pin number 1 from the sensor goes to the header place number 3. The ground pin of the sensor, the middle one, goes to header place number 4. And the signal pin from the sensor goes to the other side of the header. The motor connector is more simple. The red pin goes to the header place number 1, which is the one marked with the arrow, and the other one goes to the other place. The turn signal switch board has 3 wires. The important one is to make sure the center, the ground pin, is in the middle. The other 2 are not important. And that's it. And here are all the parts needed to complete the steering pad 900F. To make sure all components are functioning correctly, I have this test code. This code also shows me some information I have to set up in the firmware of the controller. More on that later. For now, I need to install the Arduino IDE downloaded from the Arduino's website. This software allows me to program the Pro Micro board easily. Once installed and opened for the first time, it goes online, updates some components and installs some devices. It takes some time and I just allow everything. When all the work is done, in the Documents folder there is a new Arduino folder. This is where the projects and libraries go. Inside this zip file I have some folders that need to be unzipped to the Arduino's folder. If there are already some Arduino projects and libraries, this might affect them. I need to make sure the libraries I'm using won't change what I already have. The most likely incompatibility is with the joystick library. I'm using one with support for force feedback, but it has the same file name as another one without force feedback. If the non-force feedback version is present, it needs to be backed up and removed from the library before trying to use the one I'm sharing. I believe the one I'm sharing works fine with sketches expecting the other, it just has force feedback added, but tests might be needed to ensure that. Once the files are present in the Arduino folder, I open the steering Pad 900F board 3 test, change the board to Arduino Micro if it didn't happen automatically, and upload the code by pressing the arrow at the top. This takes a few seconds, and after uploading, it is possible to see on the display some information. A row of zeros representing each physical button, a number showing the reading of one of the analog switches line, 3 numbers showing the readings of the sensors. If I pick up a magnet and change the polarity next to one sensor, I should see the reading changing over time. If it doesn't change, the sensor might be unplugged, the pins could be in the wrong location, or the sensor could be damaged. It is normal to see some noise, small changes in the last digits, because of the prototype nature of the board, but if the numbers are not changing at all, the ADS might have a problem. The number on the middle line shows the reading of the buttons combination. 1023 is the value expected if none of the buttons are pressed. These readings belongs to button 3, 5 and 6. Pressing each button gives a different value. In the script, there is a constant array called thresholds with 7 numbers. Each number represents one button or a combination of buttons. The next step is to confirm the numbers are the same, because this will depend on the quality of the components. Pressing button number 3, I get 236. And I put that number in the first position of the array. Pressing button 5, I get 394. That goes into the second position. Button 6 goes in the third position. Button 3 and 6, this is a combination, go into the fifth position. And now you get the idea. I follow the combinations in the comments right after the numbers and update all of them. This process sets up the resistors on the board, telling the Pro Micro what value to expect. Once all combinations are done, I upload again and update the code. If the first line wasn't responding before to the buttons pressed, now it should. Every 0 represents a single button and all must change to 1 individually when the corresponding button is pressed. If the motor is connected, button 1 and 2 should also make the motor rotate to one side or the other. At this point, if everything is responding as expected, it's time to start assembling the controller. This thresholds array has to be copied to the final firmware, but that is for the firmware upload video. Now that all the components are ready and functioning, jump into the next video about the assembly process and see how I put everything together, almost ready to use. And for now, thank you for watching, like and subscribe, and I hope to have you in the next video.